Okay. Welcome to this live session on this 24 2006 IPM. So today we'll be starting. Uh, we are in week 10. Okay. So this week 10 and 11. Okay. So they deal with this state variable analysis. Okay. So where we'll have week 10 as. So what exactly a state variable means? It can deals with these topics. Okay. Then what are the state space equations? What are state space equations? Yes, you are asking something. Uh, if we have any doubts in the previous week, can you ask at the end of the session? Yeah, yeah. Okay. So what are these state space equations? Then how to form these state space equations for a given problem. So after that, so state transition matrix, state transition matrix, then transfer function. We already know about transfer function, but to transfer function in view of this state space equations, okay, then linearization. Okay, so these are the topic discussed in week 10. Since week 11 also as part of this state variable analysis, it is good to know these topics also. Week 11, so it discuss about the controllability and observability. Okay, controllability and observability. Then, so we'll have something called as the pool placement technique. Okay, then observer design, or you can say state observers. Okay, so finally we'll have Kalman filtering also. Okay, these are the topics of week 10 and week 11. So assuming that these are all part of this state variable analysis. Okay, so let us try to understand one by one, and we'll try to see one example for each topic also, so that you will understand, you will have the better understanding. So let me show my slides. So if you're getting any doubt, you can ask me directly. Okay. So basically, any systems, any linear dynamical systems, okay, so their operations, okay, we can represent by using set of differential equations. For example, if you take up any electrical circuit, okay, any electrical circuit. So generally what we do when we have electrical circuit, okay, so generally what we do in we have electrical circuits, we will write either KVL or KCL equations, correct? KVL or KCL equations. So when we see AC circuits, like when the circuits particularly consists of these inductors and capacitors, okay? So if circuit consists of only resistors, voltage source, current sources, okay, you will not have derivatives and integrations, okay? But when your circuit consists of inductors and capacitors, okay, so you will get uh, your KVL and KCL equations are in terms of the integral differential equations, correct? So integral differential equations, it means that you'll get combinations of both the integral and differential equations. Okay, so this is what is the meaning of set of differential equations. Okay, so basically those equations will govern the system behavior. Just a minute, somebody was asking down. We can do an example question similar to design assignment. Easier to do the assignments in the MATLAB at the end of the session. Which design experiment you are asking?
Sir, so far we have only received a design assignment one. Like
Okay.
previously we had MATLAB in digital signal processing, and sir used to do like an example. There used to be like 4 or 5 every week, and sir will do 1 or 2 questions and we will do the rest. So you will get an idea of how to work in MATLAB with the new.
Oh,
There are
okay,
like so
okay,
many for
okay,
MATLAB, there are so many functions, right, sir? So here I was like finding it difficult to find the exact functions or different things we have to use. So if we are doing any
okay,
similar example, it will be very
okay.
useful.
You're asking like how to use the control system toolbox. Is that
Yes,
your
sir.
doubt?
Yes, sir. How
Oh,
to
okay, okay.
exact functions to use, and like how to find the how to highlight the what is it cutoff
Yes,
frequency
yes,
and
understand, understand. So
overall
that you
all
can do
that
the design experiments
overshoot.
better. Okay.
Yes, sir. Yes, sir.
What we will do is we will take up that part on Wednesday. Why? Because currently we have to install MATLAB and so come up with the exact
Okay, okay, sir.
problems. So
So
because
submission was extended, right, to Wednesday
this
for
one,
the first week? For the first week, submission is extended to Wednesday, right?
the week 9
No, sir. Design assignment.
design assignment 1.
Yes, sir.
I'm not verified yet. So I'll let you know in the discourse. I'll verify and let you know.
Okay, sir. Okay.
Okay. Yeah, yeah. Okay, so now any system, either it is a electrical system or mechanical system or social system, any system, their operations or their behavior, uh, we can write it in terms of the integral differential equations. Okay, so basically these integral differential equations or this set of differential equations. Okay, so uh, basically the state is nothing but what? State is the uh, it is defined as the set of physical quantities. Set of physical quantities that basically specifies the evolution of the system completely. Okay, so you can understand it easily. Suppose if you see that any electrical circuit, okay, so uh, electrical circuit, if it is having inductor and capacitor, okay, so they basically those two will reflect the evolution of the overall circuit to behavior, correct? So we basically depends upon we define the state based upon these two parameters L and C. Okay, so when we take up this example, you will understand what exactly the meaning of this state, the practical meaning. Okay, so again you can see, so it is the set of physical quantities. Okay, so that come using those quantities you can specifically define the overall system behavior. Okay, for any given system, it is the electrical, mechanical, any system. Okay, so the physical quantities may not be unique, but number of physical quantities has to be unique. It means that number of states has to be, for a given system, states has to be fixed. Okay, it will not vary. Clear? So that is the definition of the state. Okay, so in any general system, so we could represent that general system using this kind of nth order differential equation. Okay, so d xi of t by dt. Okay, so then you will have f of the state and input. Number of states are x1, x2, etc. xn. Inputs are r1, r2, etc. rp. Okay. Similarly, the output could be represented like this. You'll understand exactly the meaning of this. Okay. So just wait for a moment. So now, if you define this x of t as a state, okay, this as input and this as output. So you could represent these two differential equations, okay, differential equations in this form in general. Okay, so dx by dt uh, equal to f of x comma r, c is equal to g of x comma r. Okay, so this is in general system for a general system. So when you consider linear system, Okay, when you consider if your system is linear, okay, those two equations, these two equations in general, they'll be represented like this. They'll be represented like this. So dx by dt equal to, so ax of t plus br of t, c is equal to dx of t plus er of t. So first one is called as the state equation. Second one is called as the output equation. So this entire system is called as the state space representation. State space representation. Okay. These are the matrix orders. These are the matrix orders. Okay. Anyone having any doubt here? So in general, so if you look at the system behavior, okay, so any system could be represented in this way, general system, okay. If the system is linear and time invariant, so they will be represented in this direction, in this form. X dot is equal to, so this also can be written as x dot is equal to ax plus du. So y is equal to cx plus du. So both are right. Okay, here in place of x we have x of t. In place of u we have r of t. Okay, y is nothing but c. Okay, so any terminology is correct. Okay, so where a b c d. Let me continue the same thing. Okay, so where a b d e are the matrices of the state space system. Okay, so what we do is generally, as I said, first when we see the system behavior, okay, so when we write, for example, electrical circuit, okay, if we write KVL and KCL equations, we will get integral differential equations. Once we have these integral differential equations, okay, we write those differential equations in this form, which is nothing but state space representation. It means that we specifically get these matrices. Okay, that we call it as a state space representation. Okay, so how we got this one from this? So general systems are generally a nonlinear systems. Okay, so this is for linear system. Okay, so how to convert a general nonlinear system to linear system? It means that this is a nonlinear system, this is a linear system. Okay, so this process is called as the linearization. Okay, this process is called as the linearization. That's one of the topic already discussed in the video. Okay, in next class we are going to solve some of the examples. Okay, next live session. Okay, as of now, just assume that so you already know the linearization. Okay, so is this clear? First, what we do is we will solve one example so that you'll understand much better what exactly we state and how to write the equations, convert them and put them into the state space representation. Okay, so let me take one example and help it. Okay, so example, let's take simple RLC circuit. Okay, so RLC. Okay, so here let's say we have V of t. Okay, so the current is the I of t. Okay, so let us say this is V naught of t. Okay, here we have three elements, resistor, inductor, and capacitor. Okay, so let me take this is as Vi. Okay, so let's say the input is this is the input. I'm applying input voltage, and this is the output I'm interested in. Okay. Now, what is the KVL equation? Can anyone tell me? KVL equation is Vi of t equal to R I of t plus L di of t by dt plus Vc of t. Am I correct?
Yes, sir.
Yes, sir.
Right. So now from here, so basically, as I said, first we write the differential equation of the system. Okay, this is the differential equation which governs the system. Correct. So now, next step is to choose the state variables. State variables are states. Okay. So generally in any system, so to choose the state variables, that is the minimum number of variables you choose, those minimum number of variables will talk about the entire system operation. Entire system operation. Okay. So it means that, so hope we have the idea of degree of freedom. Okay. Degree of freedom is that's the same definition. Okay. The minimum number of variables you will use to explain the system behaviors. In any general system, either electrical, mechanical, physical, social, any systems, there are something called as the energy storing elements. Energy storing elements. So basically, if you know the behavior of the energy storing elements, they explain everything or the whole evolution of the system behavior. What are the energy storing elements here? So inductor and capacitor. Am I correct?
Yes, sir.
Yes. So in that case, number of state variables is 2. Okay. So this is the first step. Okay. Number of state variables. Then what are the state variables? Let's say state variables x1 and x2. Okay. So x1 and x2. Basically, when we see inductor and capacitor, okay. So inductor behavior basically changes with what? Inductor behavior basically we talk with what? We'll say that current. Am I correct? Capacitor with its voltage. Yes, basically this is what we talked about, because inductor energy changes with current, capacitor energy changes with voltage. That is how we will choose these state variables. Now, number of state variables are 2, which is the equivalent to the energy storing elements. So these are the state variables. Is this clear? Any queries?
Sir, for if circuit is having two inductor means the state
Yes.
variable is 3, sir.
3. Okay.
Okay, sir.
So that 3 has to be fixed. Okay. The state variables, you can choose anything. Okay, not necessarily IL and VC, or you can also choose different things. Okay. And also, why can't I choose X2 as IL and X1 as VC? That is also possible. Is that clear? Because you will get this
Yes, sir.
doubt at the end of the question, because the matrix elements are different. A is not equivalent to sometimes A transpose. Okay. So that kind of doubt you'll get. So here I'm clearing that doubt here itself. You can choose randomly. X1 as VC and X2 as IL also. Okay. So that is first step. Is this clear? Number of state variables. Okay. So next. So what we do is, so first, as I said, what is the state variable form? State variable form is x dot is equal to AX plus du. So y is equal to Cx plus du. Okay, where A and B are the matrices. Okay. Now, so what is x here? So our x is nothing but 2 variables, x1, x2. So which is nothing but IL, VC. Am I correct? Okay. So which is nothing but I and VC. Okay. So Now X is 2 by 1. Am I correct? X is 2 by 1. Okay. And also we said that output Y is nothing but V naught. Okay. So that means Y is what? Y is 1 by 1. Okay. So now can you write it this one like this, X dot? Can you write the uh, sizes of these matrices? Okay. Cx plus du. Okay. So what is X? X is 2 by 1. Am I correct? So here also 2 by 1. Okay. What is Y? 1 by 1. X dot also 2 by 1. Correct? So can anyone tell me what is the size of the matrix A? Anyone tell me? It should be. What is the input we have? Input U is nothing but Vi of t. So that is also 1 by 1. Correct? Now tell me the sizes of A, B, C, D. Anyone? A will be 2 by 2. Correct? Yes or no? Any doubt?
Sir, I can't understand this. How it is 2 by 2?
Is this clear?
Yes, sir.
So now
Here.
we are multiplying A and X. Okay. We are multiplying A and X. Okay. That is summing up with B and U. Okay. That has to be
Sir,
equivalent to what?
Sir, how A is 2 into 2? You are taking 2 into 2 or what?
No. See, here we are adding this term and this term, correct?
Yes, sir.
After adding, what is the overall size I need to get? This one only.
Yes, sir.
Now fix the sizes for B and A. How much it could be? How much it could be? It should be 2 by 1, correct? Yes or no? B should be 2 by 1. Then only we will get 2 by 1 here. And this should be 2 by 2. Yes or no? That is basic maths. There is no surprise, basic maths. Okay. So what is C? How much I need to get here?
1 into
1
1.
by 1. So what is the C could be? Yes or no? One by 2. Am I correct? These two are matching.
Yes, sir. Yes, sir.
Then to match with this, I'm taking 1 here. So what is here? 1 into 1. Am I correct? So now you can see that A we need to get 2 by 2, B we should get 2 by 1, C we should get 1 by 2, D we should get 1 by 1. Correct? Okay. So that's the major thing. Is it clear? Any doubt? Any doubt? Okay. So let's
No, sir.
start like this. Sorry.
No, sir. No doubts. No doubt.
Yeah. So let's start like this. Okay. Now what is the, let's write down this one first. What do we have on the left side? We need to first find the X dot. Okay, what is x dot? Okay, x dot is nothing but what? X1 dot, x2 dot, which is nothing but what? I dot, pc dot. Am I correct? So we have to find I dot and vc dot. Am I correct? Okay, so can anyone tell me what is vc of t? Voltage across capacitor equation. Can anyone tell me?
1 by c integral of I into dt.
Yes, exactly. So vc of t is nothing but 1 by c integral I of t dt. Correct? So what is dvc by dt or vc dot? What is it? Taking derivative for this. So I of t by c. Am I correct?
Yes, sir.
Yes. Okay. So this I need. Because here I require. Is this clear? Any doubt?
No,
Any
sir.
doubt? Yeah.
Yes,
So
sir.
now considering this equation, I'll write I of t expression directly. Okay. So I of t from that equation, not I of t. So directly from there, we can write this term, di of t by dt, correct? So that I'll write it is as, that is nothing but di of t by dt. Okay. So which is nothing but minus r by L I of t minus 1 by L Vc of t plus 1 by L Vi of t. Clear? Any doubt? Any doubt? Okay. So this is I of t dot. What is Vc of t dot we got? I of t by c. Am I correct?
Yes, sir.
So now look at these two equations and put it in the matrix form. Okay, I'll write it like this. So I of t dot left hand sides Vc of t. Okay, so I'll write it like this. I of t Vc of t. Okay, so Vi of t. Okay, now look at the second equation. What do we have? In the second equation, what do we have? So I of t multiplied by 1 by c, correct? So I write it like this. I'll keep it 0, here 0. Can you check it now? Am I correct? Second equation. So look at the first equation. So I'll write it like this, minus r by L minus 1 by L, okay, plus 1 by L. Now can you check it now? Are both the equations are satisfying? Yes or no?
Yes, sir.
Yeah. So now you could see how does this looks like? X dot.
Sir,
Yeah.
for VIT, uh,
Just
as
a
the
minute.
equation is second equation, you wrote 0 in second row.
Here. Yeah, I understand. This one. Yeah, tell me.
For IT, I dot T is equal to, that is 1 by L VIT. So you are writing 1 by L in the above. That is
Yeah, that's correct.
Yes, sir.
That's correct only, no?
Yes, sir. Understood.
Get multiply it and check it. Okay.
Yes, yes.
So now this is nothing but x dot a X, P, U. Okay, so those dimensions also will match. Now, okay, what is your output? Y is equal to, okay, so that is nothing but V naught of T, which is nothing but what? V naught of T is nothing but Vc of T only. That is nothing but Vc of T only. So this, how could I write? Okay, so put something and again, so I of T, Vc of T. Okay, I of T, Vc of T. So simply I can write it like 0, 1. I'll get Vc of T because this multiplication, this and this and this. Okay, so how does this one looks like now? This one looks like Y equal to C X plus D U. Okay, where D is zero matrix. Okay, something like I can add here 0 V of T. Is this clear?
Yes, sir.
Clear, sir.
Okay, now you got ABCD matrices. Okay, where this is A matrix, B matrix, C matrix, D matrix. Okay, this is called as the state space representation of the electrical circuit. Okay, so given first what we need to do is first we have to write differential equation. In this case, using KVL and KCL, we are writing this differential equation. Okay, then define the state variables, number of state variables based upon the energy storing elements. Okay, then define them properly. Okay, then so simplify the equations properly and try to get these two equations. Okay, finally put them in the matrix form and check what are your final ABCD matrices. This is called as the state space representation of this circuit. Clear? Any doubt? Any doubt? If you have any doubts, you can ask me.
No doubt, sir.
Yeah. Okay, even though okay, so now the question. Okay, so suppose if you take these two rivers, okay, what will happen? You will find these two rows rivers, correct? Am I correct? You will find these two rows rivers. Okay, so obviously the A matrix changes. A matrix changes. Am I correct? A matrix changes. Okay, in examination, one student may take first case, second student may take second case, but both answers are right because the final answer it will be same. Final answer. What do you mean by final answer? Final answer means using state space representation, we might find the transfer function. Okay, from the transfer function, we might find poles and zeros and do the further analysis. Those answers will not change. Is this clear? So whatever the order you take, it does not matter. Okay. So this is the basic introduction to the state space representation. Any doubt? Okay, if there are no doubts, we will shift to the next one. So as I said, that is the basic example, writing the system into this one. So this is for electrical circuit. Okay, so you could do the same thing for mechanical systems. So the other any social systems, so like game theory problems. So some of the examples sir has already explained in the videos. Okay, you could watch them. Okay, yeah. Next, state transition matrix. Okay, suppose in that in this equation, if you consider only the homogeneous part, why we are calling that is as homogeneous? Here R of t is the input. Okay, without input, we call these systems are only this part is first part is called as the homogeneous. Okay, so homogeneous part of the equation. Okay, so now state transition matrix is something, okay, so which satisfies this equation. Okay, what is that? X of t. Okay, so it satisfies this equation, we call that is as the state transition matrix. For example, that state transition matrix is phi of t, for example. So if you substitute that, so you will get d phi by dt a phi of t. Okay, so then if you start your system at x of 0, initial state, okay, your x of t will be like pi of t x of 0. Okay, so the question is how to find this pi of t. Okay, so now you have already this x dot is equal to ax plus bu. Am I correct? Sorry. You have this equation you have considered is x dot is equal to ax. Okay, so what if you apply the Laplace transform on both these sides? What you get? Laplace transform of dx by dt. What is it? This term. Am I correct? Yes or no? Laplace transform of derivative. S x of s minus x of 0. Correct? Equal to ax of s. Am I correct?
Yes, sir.
Yeah. So from this now, so you can bring this x of s this side and get x of s is equal to, so si minus a whole inverse x of 0. Any doubt here in this? Any doubt?
Sir, what is
Okay.
that I, sir?
Multiplication. This is identity matrix. Why? Because we are not dealing with the single variables. Usually what happened here, x is not a scalar. X is not a variable. It is a vector, correct? Because we are dealing with the x is what? You have seen the example. x1, x2, etc., xn, correct? Yes or no?
Okay, sir. Clear, sir.
Yeah. What is x0 means? X0 is also a vector, correct? So x of s is means what? So that is function of s. Okay, it has to be equal to this. So that's why we are multiplying with I, identity matrix. Okay, so now from this, so anyone tell me, so how can I find x of s, x of t? How can I find x of t? Taking inverse Laplace
Inverse
transform.
Laplace transform.
Yes.
Okay, so what is x of t is equivalent to? Laplace inverse of si minus a, Laplace inverse of si minus a whole inverse, correct? Multiplied x of 0. Am I correct? Because x of 0 is a constant initial condition. Okay. Yes or no? Now this can be written as x of t is equal to some pi of t into x of 0, where pi of t is nothing but Laplace inverse of si minus a whole inverse. Okay, is it clear now how we got this pi of t? Clear?
Yes, sir.
Yes, sir.
Yeah. So this is called as the state transition matrix. State transition matrix. This is what we have considered here. Okay, so that also you can see. So this expression, so this particular term is called as the state transition matrix. Okay. also you can write it, because we said that what is the equation we have considered. So dx by dt equal to ax of t, correct? Yes or no? What is a here? A is a matrix. Am I correct? Yes or no?
Yes, sir. Yes, sir.
Right? What is x here? X is a vector. Correct? So now instead of this, I'm taking simple case dx by dt equal to ax from calculus. Dx by dt is equal to ax, scalar case. So where here small a is small number, okay? X is not a vector, x is just a variable. What is the solution of this? Can anyone tell me? What is the solution? What is the solution? How do you find the solution for this? Dx by x equal to a dt. Am I correct? Variable and separable. Take integration on both the sides. Ln x plus c equal to at plus c. Correct? Not ln x only here. Okay. So ln x equal to at plus c. What is x? E power at plus c. Okay. What is x? E power at multiplied e power c. What is it? X of 0. What is it? E power at x of 0. Am I correct? This is how you'll find the solution in maths. Is that correct? This is scalar case. Right? Am I correct? So what is the solution for this? What is the solution? X of t, if scalar solution is this, what is the solution for this matrix case? E power capital AT x of 0. Am I correct? Yes or no?
Yes, sir.
So that's what this one, another solution. Okay. Now what is e power x? E power x is 1 plus e power ax. E power small at. 1 plus small at 1 by 2 factorial a square t square etc. That is how you can write. This is also another way. This is also another way. But mostly what we do is to find pi of t, we use this one. Clear? State transition matrix. Okay, any doubt? Okay, basically state transition matrix, what it says, x of t equivalent to pi of t multiplied x of 0, correct? Correct? Okay, so what it says basically, if you know your pi of t and initial condition, you will get your this is initial state. Okay, if you multiply that initial state with state transition matrix, you will get your next state. Yes or no?
Yes, sir.
Okay, so basically your pi of t is taking your state from x of 0 to the next state at t. Okay, that's the meaning. Okay, so that you can see here. Okay, that you can see. When you don't have any state transition, pi of 0 is I. Okay, so taking, if you start from here, it takes to the next state t1, next state T2. That's the meaning. You don't need to by heart this. That's the meaning of the state transition matrix. Okay. So now consider the full equation. So previously we have considered, is this clear? Any doubt? Any doubt in this equation? Getting the this expression? Any doubt? Any doubt? Okay. So now we have started with this equation, homogeneous without input, and we got that state transition matrix. Now let us start with the full equation. Given equation, state equation. Okay, so x dot is equal to ax plus br, y is equal to cx plus dr. So this is called as the state equation. This is the output equation. Okay, so we are considering the state equation. Okay, now in this, if you take the Laplace transform on both these sides, okay, what is on the right side, left side? Laplace transform of the derivative. Yes, x of s minus x of 0, correct? Okay, so here ax of s plus b r of s. Okay, so bring the x of s only this side and take the other terms that side. Okay, so you'll have si minus a whole inverse x of 0, si minus a whole inverse multiplied b r of s. Okay, is there any doubt here in this equation? So let me write it. Okay, so yes, x of s minus a x of s, I'm bringing that equal to x of 0 plus b r of s. Okay, so just bringing that a x of s this side. So x of s I'm taking out. So I should write s minus a equal to x of 0 plus b r of s. Okay, since s is the number, s is the just a variable, a is a matrix. So that's why I'm multiplying with I, okay, which is equivalent to the order of a. Then the matrix equality verifies. Okay, then x of s equal to, when this si minus a, which is the matrix, goes that side, it will become inverse. X of 0 plus b r of s. I've got this equation from here. Is this clear? Clear? Any doubt? Any doubt? If you're not
No,
clear,
sir.
you can ask me.
No,
Yeah.
sir.
So then we are taking the inverse Laplace transform because we are interested to find x of t. Okay. So this term we already know. What is this term? Phi of t, correct? So again, this term, okay, this term, what is this? Phi of t, okay. What is this? R of s. Okay, can anyone tell me, okay, why we wrote like this integral? Can anyone tell me? Can anyone tell me?
Sir, time shifting.
Time shifting. Okay, why time shifting? Anyway, this is the point. Laplace transform of f star g. Star indicates the convolution. F of s multiplied g of s. Correct? Yes or no?
Yes, yes, sir.
Right, what we are doing here, we are taking inverse Laplace. So it will become convolution. Inverse Laplace of this will become convolution. So finally, what does this indicates? What does this indicates? Can anyone tell me what does this indicates? If you just know your A matrix, if you know your A matrix, you can find pi of t, correct? Pi of t is nothing but what? L inverse of Si minus A whole inverse. Am I correct? So if you know your A matrix, you can find pi of t. Then if you know your B matrix, directly you can find the whole x of t, correct? State for all the times t is greater than or equal to 0. Am I correct? Given the initial condition. Given the initial condition. Is this clear? Okay, so you'll understand this. We are going to solve a problem. Okay, so now, so when if in place of 0, if you just substitute t is equal to 0, this is our equation. Okay, so we have this x dot is equal to ax plus, so br, y is equal to cx plus dr. Okay, once you know x, okay, once you know r, okay, here already know your x, so then c is nothing but this y. Okay, that is nothing but this equation. You can directly substitute x from here, so you will get this equation. There is no surprise. Okay, any doubt in these two equations? This already we have seen. Simply we are substituting x of t in place of here, you get this equation. Okay, only the notations are little different. Okay, so now what we saw in last 5 minutes was, so we have considered the homogeneous equation and found the expression for state transition matrix, L inverse of Si minus A whole inverse. Okay, then considered the full equation. Okay, and finally found the expression for state x of t. Okay, these are the two steps. Let us do some example, you'll understand it. Okay, now you see, this is the example, state transition, state space representation of some system. Okay, so is there any doubt? Is there any doubt here in this equation? Because just now we saw one example for circuit, how to, for any system to get the state space equations. Okay, there should be a plus here. Okay, these are the, this is x dot A, okay, B. Okay, is there any doubt in this? Okay, so now you know AB matrices. Okay, this is A matrix, B matrix. Okay, so this is the state transition equation, state transition matrix equation. Okay, is there any doubt? Our intention here is, when input is unit step, okay, so we wanted to find x of t. That is our question. When r of t is unit step, we wanted to find x of t. Okay, is question is clear, everyone? Question is clear? So state space representation is given for a system. It could be electrical circuit or mechanical circuit, anything. It is the state space representation. Somebody wrote and gave it to us. Okay, so previously we saw how to write these state space model for electrical circuit. So assume this is for something, some system, maybe circuit or some system. Okay, so given this, okay, then unit step input, r of t is unit step. In that case, what is the x of t? That is our question. Okay, so now first step is, we will be finding this state transition matrix. So basically we divide that problem into parts. Okay, we have to take L inverse Si minus A whole inverse. First we take Si minus A. S is just a number, okay, variable. So multiplied I, okay, and A matrix. You have to take the I matrix order exactly same as that of the A. So this is Si minus A. Is there any doubt in this? Any doubt?
No, sir.
Yeah. So once we have that, what is our next step? Take the inverse. Take the inverse for this matrix. Okay. You already know how to take the inverse for a matrix. Okay. So how to take inverse for a matrix? A inverse is what? Adjoint A by det A. Am I correct? Adjoint A by det A. So this is the det. This is the det. Okay. And this is the adjoint. Adjoint of Si minus A. This is the det of Si minus A. Okay. So we got inverse as this. Okay. So you please do these calculations finding inverse. Hope it is not difficult. Okay. So now what is next step? Once we have the inverse, you should take the L inverse. So take L inverse. L inverse for each term. Laplace inverse, we have already seen our first classes. Okay. L inverse for each term. So now tell me, what is L inverse for this term? L inverse for this term. Okay. So individual terms again. That is 2 e power minus t minus e power minus 2t. Yes or no?
Yes, sir.
Yeah. So similarly for all the terms. So this is your pi of t now. Pi of t matrix. Any doubt in this? Finding state transition matrix. Okay. Given AB, given state space representation. In state space representation, you can find this pi of t, state transition matrix. Okay. Now our question is, if the R of t is unit step, what is x of t? Okay. So now we are going to use this equation directly. Okay. Equation directly. Okay. Now you can see this. This is the equation we have. Okay. So substitute everything. Okay. So x of t, once you substitute first part, what will you do? So x of t is equal to, what is your pi of t? Pi of t is this matrix. Okay. So pi of t minus t naught. Okay. So substitute into this equation. This is first step. Okay. This part only. Is it clear? Any doubt? This term clear? This is x of t naught. This is x of, this is pi of t minus t naught. Any doubt? And why r of tau is 1 here? Why r of tau is 1 here? Because it is given in the problem. Input. Is this clear? Next. So the second term, this term. So plus second term is pi of t minus tau b r of tau. So this entire term is pi of t minus tau. Okay. B. Okay. R of tau is already 1. R of tau is 1. Is this clear? This step? This step clear? Okay. Simply you are using pi of t here. properly. Okay, now you can see that. So the rest is calculations only. Okay, so this term as it is, it's carry forwarding. Okay, so you are doing some simplification here. You are multiplying pi of t minus tau, this matrix, with 2 by 2 with 2 by 1. Okay, so you will get this one, 2 by 1 multiplication. Okay, so if you forwarding all these calculations, okay, simplifying all these calculations, okay, so the final expression, okay, so you will have only 2 by 1, 2 by 1. Okay, first row gives you this, second row gives you this. Why? Because this side what do we have? X of t only, that is x1 of t, x2 of t. Clear? So these two, first row gives you this, second row gives you this. Is this clear? Is this clear? Any doubt? Any doubt? Any doubt?
No, sir.
Yeah. So next. No, there is no doubt. Okay. So
Sir, we have to
next,
find the xt. We have to find the value of two, x1t and x2t.
yes. That's our question.
Yes, sir.
That is our question.
Okay. Yes, sir.
Okay. Next. Okay. Next is I'll quickly finish this transfer function. Okay. So what do we have? X dot is equal to ax plus bu. Y is equal to cx plus du. Okay. Where here x is the state, u is the input, y is the output. Let me write it. X is the state, u input, y output. Basically, what is the transfer function? Transfer function, what is the definition?
The input, output by input.
Output by input. What is that? Output by input means y by u. Okay,
Yes,
let's
sir.
try to find that. So first, let us consider this. Apply the Laplace transform. What do we get? Yes, x of s minus x of 0, correct? Is
Yes,
equal
sir.
to a x of s plus b u of s, correct? Yes or no? Okay. So now bring that s x of s minus a x of s equal to b. Let me write it here. Yeah. Okay. So b u of s plus x of 0, correct? So I can write this one as si minus a x of s is equal to, so b, I'll write it in the reverse way. Okay, so x of 0, okay, plus x of 0 plus b u of s. Okay, so what is x of s? Si minus a whole inverse x of 0, si minus a whole inverse b u of s. Am I correct? Yes or no? Okay, so let us consider this is a 1. Now consider this. What is y of s? Y of s is c x of s minus d u of s, correct? Right?
Yes, sir.
Yeah. Okay, so right. So now substitute this x of s there. Our intention is to find this expression. What is the y by u? Okay, c multiplied. So I can write it directly. C multiplied Si minus A whole inverse x of 0. Okay, plus what is it next? We are multiplying with C. Okay, plus C multiplied Si minus A whole inverse B U of S. Correct? Am I correct? Yes or no? Plus D U of S. Right?
Yes, sir.
We missing anything? So how do we find yeah. So yes. So let us say consider x of 0 is equal to 0. Okay. So all initial conditions are 0. If all initial conditions are 0, this term goes to 0. Correct? If that term goes to 0, okay. So what is y of s is equivalent to if you see Si minus A whole inverse B plus D U of S. Am I correct? What is finally y of s by u of s is C Si minus A whole inverse multiplied B plus D. Is it correct?
Yes, sir. Correct.
This is the transfer function. This is the transfer function. If you just know your A matrix, B matrix, you know your A matrix, B matrix, C matrix, D matrix. What does it mean? Given x dot is equal to Ax plus du, y is equal to Cx plus du. Given state space system, you can find the transfer function. Clear? That's the meaning. Okay. So now you see, given ABCD matrices, you can do all these calculations. Can you do all these calculations? Yes, sir.
Yes, sir.
Yeah. So, okay. So we'll stop here. Okay. And continue the same thing in the next class. So let me give some surprise test. Okay. So write down the state space equations for this problem. So I'm giving little big one. So 3 energy storing elements. Okay, so L1, L2, R2, R1, U of T, C plus minus VC. Okay. Yeah, so this current is I1, this current is I2, this is VC. Let's say this is Y. Yeah, output. Okay, Y of T. Okay, so the question is write state space representation. state space representation for the circuit. Okay.
Sir, right state.
State space representation.
Okay.
State space representation means this form only. X dot is equal to AX plus du, y is equal to CX plus du. So we have already written for the first example in this form. So it means that you have to write your KVL or KCL equations, anything, whatever you want. Okay. So find the number of states. So energy storing elements, write down the equations properly, identify the state variables. Okay. Find their derivatives. Okay. Finally, put them in the matrix form. This is called as the state space representation. Okay. Yeah. So we have 20 minutes time. So currently the time is 6:16. Okay. I can submit it by 6:40. Okay. Yeah. Thank you.
Sir.